Converse of the Basic Proportionality Theorem. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already mastered. In our previous lesson, we studied the Basic Proportionality Theorem, or BPT. As you remember, that theorem tells us that if we have a line drawn inside a triangle that is parallel to one of its sides, that line will divide the other two sides into proportional segments. Now, today we are going to flip the script and explore the inverse of that logic. Instead of starting with a parallel line and finding the ratios, we are going to look at the converse of the basic pro-parallelism theorem. This is a powerful tool because it allows us to work in the opposite direction. It gives us a way to determine if a line is definitely parallel to a side of a triangle, simply by looking at the ratios of the segments it creates on the other two sides. Let's see how this works in practice. Understanding the concept. Think of the converse of the BPT as a question. If you are looking at a triangle and you notice that the line cutting through two sides is dividing those sides into exactly the same ratio, the big question is, can we confidently conclude that this line is parallel to the third side? And the answer is a definitive yes. To help you keep this straight in your mind, I want you to look at the direction of the logic. In the BPT we studied previously, we started with the fact that lines are parallel and used that to find the ratio, so we move from parallelism to proportionality. But with the converse, we are reversing that flow. We start with the known proportionality of the segments and use that to prove parallelism. It is essentially the logical mirror image of what we learned in the last lesson. Now that we've recalled what the basic proportionality theorem tells us, let's really dive into the core concept here on slide 2. Formal statement of theorem 6.2. The theorem states that if a line divides any two sides of a triangle in the same ratio, then we can conclude that the line is parallel to the third side. To make this mathematically precise, let's look at the representation. Imagine we have triangle ABC suppose a line, which we'll call DE, intersects side AB at point D and side AC at point E if the ratio of the segments on the first side, specifically a D over DB, is equal to the ratio of the segments on the second side, a E over EC, then we have a very important result. It must be that the line DE is parallel to the base, BC. Now that we've established the conceptual difference between the original theorem and its converse, let's look at the formal statement of theorem 6.2. Keep this specific ratio in mind, because in the next few slides, we are going to use this exact mathematical setup to walk through a formal proof using the method of contradiction. Step-by-step proof. Now that we understand what the converse of the basic proportionality theorem actually claims, let's look at how we can actually prove it. The most effective way to tackle this proof is by using what we call the method of contradiction. Now, don't let that term intimidate you. Essentially, the strategy here is to start by assuming the exact opposite of what we are trying to prove. We will pretend that the line is not parallel, and then, through logical steps, we will show that this assumption leads to a mathematical impossibility or a contradiction. When the assumption fails, we are left with the only remaining truth, that the line must be parallel. To set this up formally, let's look at our given information. We have a triangle, ABC, and a line, DE, drawn across it. We are starting with the premise that the ratio of the segments on one side is equal to the ratio of the segments on the other side. Specifically, the ratio of AD to DB is equal to the ratio of I to EC. Our ultimate goal, or what we to prove, is to demonstrate that the line DE is parallel to the base, BC. Keep this goal in mind, because in the next few slides, we are going to use a clever construction to show that assuming the line is not parallel simply doesn't work. Step-by-step proof continued. Now, to move forward with our proof, we need to perform a specific construction. Remember, as we mentioned in the previous slide, we are using the method of contradiction. This means we start by assuming the exact opposite of what we want to prove. So, let us assume that the line DE is not parallel to the base BC. Now, if this line DE is not parallel to BC, there must be some other line passing through point D that is parallel to BC. Therefore, we will draw a new auxiliary line, which we'll call DE prime, starting from point D and extending until it hits the side AC at a new point, E prime. By doing this, we have created a scenario where DE prime is parallel to BC, which will allow us to use the basic Proportionality theorem in the next step to see if our assumption holds up. Step-by-step proof, logical steps. First, let's look at step 1. Because we specifically constructed the line DE prime to be parallel to the base, BC, we can now use the tool we already know, the Basic Proportionality Theorem. By applying BPT to this new line, we can state that the ratio of the segments on the left side is equal to the ratio of the segments on the right side. In mathematical terms, the ratio of a D to DB equals the ratio of a E prime to E prime C. Let's label this as our first equation. Next, in step 2, we bring back the information we were originally given at the start of the problem. Remember, the problem statement explicitly tells us that the original line, DE, already divides the sides in a specific ratio. Specifically, the ratio of a D to DB is equal to the ratio of a E to EC. We will call this our second equation. Now that we have introduced our construction in the previous slide, where we assumed the line was not parallel and drew a new line, DE prime, to act as our parallel reference, let's move into the logical heart of the proof. Now, keep these two equations in mind, because in the next slide, we are going to compare them to see what happens when we set them equal to one another. Step-by-step proof, logical steps continued. If you look at step 3, you'll see that since both the ratio of a D over DB and the ratio of a E prime over E prime C are equal to that same initial ratio, they must, by logical necessity, be equal to each other. So, we can state that a E prime over E prime C equals a E over EC. This leads us to a very important moment in our proof, the analysis. Look closely at the line segment AC. We are looking at two different points, E and E prime, both dividing the segment AC into the exact same proportion. Now, think about this logically. Is it possible for two different points on the same line to divide that line into the same ratio? The answer is no. For these two ratios to be identical, the point E prime must actually coincide with, or be the exact same point as, point E. In simpler terms, E and E prime cannot be two different locations. They must be one and the same. This realization is the key that allows us to reach our final conclusion in the next slide. Now, let's bring our logic together. In the previous slide, we established two separate equations. On one hand, we have the ratio from our construction, and on the other, we have the ratio given in our original problem. Step-by-step proof, conclusion. Now, let's bring our entire logical argument to a close. In the previous slide, we analyzed the ratio and realized that for the segments to be equal, the point E and our constructed point E prime must actually be the exact same point. So, for our conclusion, since E and E prime are the same point, the line segment DE is identical to the line segment DE prime. And remember, back in our construction step, we specifically drew the line DE prime to be parallel to BC. Therefore, it logically follows that our original line, DE, must also be parallel to BC. And there we have it, the theorem is hence proved. Now that we've finished the formal proof, let's look at how this mathematical principle actually applies to a real-world scenario in the next slide. Real-world application, quality control in construction. Now that we have walked through the formal mathematical proof and understood the logical structure of the theorem, let's step away from the abstract equations and see how this actually works in a real-world scenario. Imagine, for a moment, that you are a carpenter tasked with building a triangular roof support. Your goal is to install a horizontal crossbeam, which we can call line DE, and it is absolutely critical that this beam is perfectly parallel to the base of the triangle, which we'll call line BC. Now, in a construction site, you might not always have access to a complex protractor or an advanced angle measuring tool to check for parallelism. However, you do have a simple measuring tape. This is where the converse of the basic proportionality theorem becomes incredibly useful. Suppose you mark a point, D, on one side of the roof so that it is 2 feet from the top vertex and 4 feet from the base. This gives us a ratio of AD over DB, which is 2 over 4, simplifying to 1 over 2. Next, you move to the other side and mark point E, such that it is 3 feet from the top and 6 feet from the base. This gives us a ratio of AE over EC, which is 3 over 6, which also simplifies to 1 over 2. Because these two ratios are exactly the same, the theorem guarantees that the beam connecting point D and point E is perfectly parallel to the base. You have achieved precision through simple measurement, without ever needing to measure a single angle. As we move to our next slide, we will look at some common pitfalls to avoid so that you don't make mistakes when applying this logic yourself. Common mistakes to avoid. First, please be careful not to confuse the basic proportionality theorem with its converse. Think of it this way. In the original BPT we studied previously, you are starting with the knowledge that line DE is parallel to BC, and your goal is to find the ratio of the segments. However, in the converse, which is our focus today, you are starting with the ratio as your given information, and your goal is to prove that DE is parallel to BC. Always, and I mean always, look closely at what the problem provides as given before you decide which theorem to apply. Second, watch out for an incorrect ratio setup. I often see students mixing up the segments of the sides. To keep it consistent, you must compare the top part to the bottom part on both sides of the triangle. You should be setting up the ratio as AD over DB equals I over EC. A very common mistake is to accidentally flip one side and compare AD over DB with EC over I. This will lead you to the wrong conclusion, so keep your segments paired correctly. Finally, if you are asked to write out the formal proof, do not skip the construction step. You cannot simply jump to the conclusion and state that DE is parallel to BC. As we saw in the previous slides, the logic of our proof relies on the method of contradiction. This means you must introduce that auxiliary line, which we call DE prime, to create the logical contradiction necessary to complete the proof. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the logic of the theorem, it is very easy to lose marks in exams by making these 3 specific errors. Keep these points in mind, and you will be able to approach these geometry problems with much greater precision. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to wrap everything up and consolidate what we have learned today. First, let's look at the core idea. Throughout this session, we've moved from simply calculating ratios to using those ratios as a powerful tool. The main takeaway is that the proportionality of the sides is a sufficient condition, meaning it is enough on its own to prove that a line is parallel to the third side of a triangle. To put this into a concrete mathematical condition that you should memorize, if the ratio of AD over DB is equal to the ratio of AE over EC, then you can confidently conclude that the line DE is parallel to the base BC. Now, if you are asked to write this out in an exam, remember the proof strategy we walked through in the middle of the lesson. We didn't just assume the line was parallel, we used the method of contradiction. We assumed the line was not parallel, introduced a construction, and showed that this assumption would lead to a logical impossibility regarding our given ratios. Finally, just remember the relationship between these two concepts. If the original basic proportionality theorem is the starting point of parallelism leading to proportionality, then the converse of BPT is its logical mirror image, where we start with proportionality to prove parallelism. Keep these points in mind, and you'll be able to tackle any problem involving these theorems. Great job today!